on Wednesday, we're going to apply today. The whole, and just to kind of remind you, yep. We're going to do this whole n is equal to 1. Ooh, that's dark. N is equal to 2. N is equal to 3. Okay, and then we have one sort of subshell here, 1s. How many boxes for 1s? One box. And how many electrons can we fix? That's an orbital. How many electrons can we shove in an orbital? 2, exactly. And then n is equal to 2, we have a 2s, 2p. So when I do these, and how many boxes for a p-type subshell? Yep, 3. When I do this, my boxes look better today than they did Wednesday. They're terrible. When I kind of picture this, so n is equal to 3, we have the 3s, 3p, 3d, so we have one box for the 3s, 3 boxes for the 3p, and how many boxes for the 3d?
5.
Yes, you got it. Oh, so smart. Okay, that sort of thing. So we're actually setting ourselves up to do this idea of where electrons are hanging out. And actually we did it for carbon, okay? And we're going to do it for things that are even a little more complicated. Talk about how we show how those electrons are hanging out in this sort of options with regard to the orbitals they can be at. Okay? So electron configurations are basically where are the electrons. Okay? And we're going to study them as if all the electrons are in their possible ground state. So the other thing to kind of remember, it's like climbing a ladder, climbing the energy ladder. So we increase energy as we go up. Okay? So they want to have the lowest amount of energy. And it's kind of weird because we can think of energy and location. Okay, this big blob down here, this is my nucleus. Okay, so not only is this the lowest energy, but this is the closest to the nucleus. And you guys kind of did some work with that today, or for your homework, I think. Okay, so how do we come up with an electron configuration? Well, there's a couple of ways, but the sure way I want to teach you first is called using the arrow diagram. And to use the arrow diagram, actually it's an application of the lowest n plus L rule. Now we have n's here. Okay, n is equal to 1. N is equal to 2 for these. N is equal to 3 for these. But what's L? Well, L, as it turns out, is the S, P, D, and F. So n is the principal energy level. So these n's are principal energies. Okay, and L then is the subshell type. So I'm just going to go ahead and tell you, because I think it doesn't have to be that complicated. In this one right here, for n is equal to 3, we picked up the D, so we have a 3s, a 3p, and a 3d. And notice how I've shown them going up in energy like this in the same principal energy level. So I'm going to kind of keep with that 3, I'll go S, P, D, and F, kind of as you're increasing energy. And actually, S has an L value of 0. So this is their L value. P has an L value of 1, D has an L value of 2, and F has an L value of 3. So these in blue are their L values. Okay? So bottom line, I can actually kind of superimpose an n plus L value for each one of these subshell types. So here we go. Okay, 1s, n plus L. Okay, n plus L. 1s, I got n is 1. What's L? 0. Yep. So the n plus L value is 1. Let's go for 2s. The n is 2. The L value is 0 because it's s. Okay. How about this one? 2 plus, what's the L value for p?
1.
It is 1. So literally the n plus L value is right here.
So you do it for each one and each in value, because you have to do like 1.
So this would be 3 plus 0, 3 plus 1, 3 plus 2. That guy right there. Yep. Is that what you said, JC?
Yeah, I just was making sure you had to do it for each level and each, each type, orbital type of each in there.
That's all it is. And what the lowest n plus L rule tells us is that as we are loading electrons, the lowest possible energy is the lowest n plus L value. And that I'm going to show you. The arrow diagram is going to unscramble this for us. Okay. So this is exactly what I told you. Do you guys remember why we don't worry? We only worry about S, P, D, and F. Why don't we worry about G and H? It just has something to do with electrons. Because they're there. They exist. It's not very intuitive. So let's.
Because they're not ground state.
Right, right. So if I look at 114, okay, atomic number 114. So that element has 114 protons. If that atom is neutral, has that many protons, has that many electrons. So we're looking at we're looking at how 114 electrons are hanging out. And to find places for 114 electrons in their ground state, you don't have to touch these guys. Now they keep building heavier and heavier elements, not discovering them, building them, creating them. We might have to actually use those. I think that's kind of neat. All right. So this is actually something we've already been talking about since Wednesday. This idea that we talked, well, let's see, how do I say that? When you have multiple orbitals, remember these guys are degenerate. Remember these are degenerate, sounds bad, but they're actually all just the same energy level. These guys are degenerate, these guys are degenerate. But when you have these subshells, we kind of talk about the energy level, principal energy level, and their subshell type. Principal energy level, subshell type. Okay, so that's all that's talking about. All right. So, N plus L rule. So these are N plus L values. Okay. And electrons will go to the lowest N plus subshell with the lowest N plus L value first. They'll completely fill that subshell, and then they'll look for the next one. So kind of as I've done it, okay, it's kind of like, well, that's an order. We have N plus L value 1, 2, 3, and actually here you're going to see if right here, see, like we have this 2p and the 3s, they both N plus L values are the same. It'll go to the lowest N first. That's the lowest energy. Okay, so these actually, as I have them written, all work. Now I'm going to go throw one more thing at you and show you why we need the arrow diagram. I hope this doesn't confuse you. When N is equal to 4, we have a 4s, a 4p, a 4d, and now we pick up our 4f. It's exciting. So I could draw boxes, but what I want to focus on over here is the N plus L value for 4s. So it's N is equal to 4 and L is equal to 0. 4p, we have 4 plus 1. 4d, we have 4 plus 2. And 4f, we have 4 plus 3. Okay, so I got 4, 5, 6, 7. Right. So we have our first sort of thing where the arrow diagram helps us out. Looking at these guys up here, okay, I buy the whole energy increasing energy, okay, here. But check this out, we have that one needs to be inserted right there. And that's the way life is. So here what the arrow diagram is going to help us do is we actually are going to load electrons in the 3p, and then we're going to skip the 3d and go to the 4s. And then we're going to go back to the 3d and then on up like that. But this actually, after n is equal to 4, we get the sort of kind of things that we need to pull in. Okay, and that's what the arrow diagram does for us. Okay. So, in order to place electrons, we're going to go at the lowest. We're going to kind of build up. So like for those 6 electrons I did on Wednesday for carbon, notice that when I was finding homes for 6 electrons, I started down here. Okay, 1, 2, 3, 4, and I need 6 electrons for carbon. So, and actually this is coming up here in a minute. I went ahead and spread them out here, so I built up. All right, so here we go. 2 ways to say how electrons are hanging out. This right here is called box for the orbital and arrow for the electron. Box and arrow notation. This is it. This is box and arrow notation. Now, this is what I call hand cramp method of saying how the electrons are configured. It gives my hand a cramp. Okay, there's an easier way. And the easier way is spectroscopic notation. Okay, and let me show you just kind of next to this how spectroscopic notation works, if that's okay with you. Spectroscopic notation for carbon would look like this. I have 2 electrons in the 1s, so I go 1s and I put a superscript 2. That 2 means there's 2 electrons in the 1s. And then I go 2s superscript, bless you, 2s superscript 2. And then I go 2p, and what's my superscript there? What is it? How many electrons? Yep, 2p2, that's it. That is for carbon, too. That's 6 electrons for carbon. How do we know how many electrons there are? By little superscripts.
So
Okay.
you have to, can you not put both of the electrons and 2p in the same box?
That's right.
They don't have to be.
They have to be what's called, I call it spread out. The Hund's rule is the spread out
So
rule.
the S and the P and the D and the F, those all represent rings? Like God
I don't think of it that way, but I know some diagrams show it that way. I like to kind of think of it linear on an energy diagram. But if you learned it that way, probably. But I'm going with what I know. Okay. So, one thing about it, sometimes students, we get busy and we don't want to, for instance, if I have 2 electrons like I do for carbon, in my 2 of my 3 possible degenerate orbitals for 2p, I have to show the empty box too. Okay, so show all the boxes and also label the boxes. Okay. And we use arrows. Okay. We talked just a little bit about Pauli's exclusion principle that says if you get down to the nitty-gritty and you're talking about a pair of electrons, I'll point to these 2 electrons in my single 2s orbital. We have a pair of electrons that are sharing a room, an orbital. One has to they have to have opposite spins, and we show that by an up arrow and down arrow. If you want to be a rebel, which everybody does, right? You can go ahead and make these down arrows. That would be fine,
That's all I'm gonna say.
because they're the only one there. But we usually say the first to arrive has got a positive spin, but it doesn't have to be. Okay, so let's look at the first, actually the first and second period of elements. So, not so surprising. Do you guys have these to fill in? There's 1 electron associated with a hydrogen atom, and it looks like that. We're not going to be rebels. There are 2 electrons associated with a helium atom, and they look like that. There, you can't be a rebel. Actually, if you put the 2 electrons with the same spin, that is a violation of quantum mechanics. So anyway, don't do that. Lithium, 3 electrons. Okay, we fill the 1s, and then we slurp over into the 2s. So this is using the Aufbau method, building up. Beryllium, 4 electrons. They look like that. So we're filling the subshell completely before we go on to the next subshell. And then we must get to boron. What did one termite say to the other termite? Boron. Now notice I'm putting like how many electrons I need to find homes for next to the spectroscopic notation that I'm working. That is a good habit. On tests sometimes, if you tell me how many electrons you're finding homes for, it makes more sense to me if you chose the wrong element. Then carbon. There we go. We've been kind of looking at carbon Wednesday and today. These are how the electrons are configured around a neutral carbon atom. This is using the box and arrow notation. So now the next slide, finally, I say what I've been saying for a little bit. Why do they spread out? Okay, it's according to what's called the Hund's rule. That is the spread out rule. Spread out if you can. Okay, I kind of liken it to if you have a big house and you have 4 kids, you give them their own room if you got enough room. Okay, if you have 4 kids and only 3 rooms, then someone's going to have to share, and that's what electrons do. Okay. Oh, sorry, I didn't realize there was more to the rule. Now, I talked about violating quantum mechanics. You can go ahead and I made these both a down spin. That was fine. But notice they will spread out with the same spin. Okay? So they're unpaired if possible. Okay? All right. So we did nitrogen, we did carbon, that was 6 electrons. Nitrogen is 7 electrons. So we fill the 1s first, and then we fill the 2s, and then need homes for 3 more electrons, and they each get their own room. Is that not fun or what? Oxygen is 8 electrons. So we fill the 1s, we fill the 2s, and then we need 4 more electrons. So I kind of think of it this way. I actually put 1 in each of the orbitals of the 2p, and then I come back and revisit that first orbital. And you might be thinking, well, could I put the electron in the second orbital? Could I share rooms for the second orbital or the third orbital? And the answer is yes. Go ahead, be a rebel. It will make me smile when I'm grading your stuff.
Like
Okay. What's that?
like my blended pizza.
Yes, exactly, like your blended pizza.
I couldn't think of another way to explain it, so I just said, I'm gonna put blended
Homogeneous mixture. Mm-hmm. So fluorine is 9 electrons. So we put the first 2 in the 1s, the next 2 in the 2s, and then we start filling the 2p. We go 1, 2, 3, and that brings us up to 7 electrons. We need to home 2 more, so we have to share rooms, opposite spins, for the first 2. And then we get to the end of the period, and the end of the period gives us the group. What's that group called? The 8A? They're called the halogens, rare gases, noble gases, exact. No, they aren't called the halogens. They're called the rare gases or noble gases.
Halogens before.
Yeah.
That's 7, yeah.
Fluorine's a halogen. And then neon is group 8A, and group 8A are the rare gases. So here we go, 10 electrons. The first 2 in 1s, the next 2 in the 2s. Then we need to house, what, 6 more electrons? Yeah, so they can all share. You guys told me the Wednesday that 6. P-type subshells can accommodate 6 electrons. So, yep. There we go, 6 electrons there. Now, group 8A, and we're going to be talking more about those actually today. Group 8A are special guys. They're called inert gases, and they have 3 names: inert gases, noble gases, and rare gases. The inert part says that they don't like to blend or play with anybody. And that's because they are really happy with how their electrons are configured. This actually is why they are inert. Okay? They end with anything that ends with a 2p6 is basically happy, done. Okay. All right. So let's look at that same set, if that's okay with you, using the non-hand cramp way. Okay. And then when we do an example here in a minute, we're going to kind of do them building up in increasing n, and then also in increasing as they are added by filling, and then rearrange them by increasing n. All right, so here we go. The one electron around a hydrogen atom looks like this. So remember, the superscripts are the electrons. So 1s is the subshell, the principal energy level subshell, and the superscript 1 is the electron.
Yeah, that's the one arrow.
That's the one
That
arrow,
would be like
exactly.
the one arrow going up.
That's exactly.
And the 1s would be like the proton, or in the nucleus.
No, the 1s is the subshell that the electron's hanging out at. Yep. There's 2 electrons around a helium atom, and they both share the same orbital. They should both share that 1s orbital, so it's 1s2. And then we get to lithium. 3 electrons. If you this should, like JC was saying, this should match up with our box and arrow notation. This is just a different notation for what we did before. So 1s2, 2s1. So you hear how I kind of pause. 1s2. Now last number I say the superscript, and then 2s, is the subshell, and then 1 is the electrons there. So beryllium, we have 4 electrons, 1s2, 2s2. So if we add up the superscripts, that's the number of electrons. Boron, we have 5 electrons, 1s2, 2s2, 2p1. Matches up with our box and arrow
Why do we
notation.
have 2 S's again?
Because of this. This is what we're working with. So you can think of it 2 ways if you want. But we have a 1s subshell for n is equal to 1. When n is equal to 2, we have a 2s and 2p. These are different subshells. Yep.
So like when we have 2s2, you're in energy level 2s, and there's 2 electrons in that.
Carbon, 6 electrons. We did this one. 1s2, 2s2. I feel like I'm playing bingo. 2p2.
And you can think of it as if it's right, you should have your subscripts add up to the number.
Exactly. Yep. Yep. These should add up to whatever. If it's neutral, actually, they should add up to the atomic number of protons, because protons and electrons are equal. And then we go on to nitrogen, 7 electrons. So 1s2, 2s2, 2p3. Then we go on to oxygen, 1s2, 2s2, 2p4. Yeah, like JC said, I add up the superscripts. I'm like, am I sure that's right? Well, if I take 2 plus 2 plus 4, I get 8. And by golly, that's the number of electrons I was after. And fluorine, 1s2, 2s2, 2p5. And then to finish it off, we get to our rare gas at period 2, and that's 2s2, rare gas, 1s2, 2s2, 2p6. Yep. Any questions about that? Cool. See, to me, you lose a little bit of information with the spectroscopic notation, because like we showed Hoon's rule where they were spreading out here with the box and arrow, and you don't show it with the spectroscopic
Yeah,
notation.
you kind of have to think of it in your mind, like there's 3 boxes, so are they going to be spread out, or are they going to be, depending on the subscript number, they could be doubled up.
Exactly. Exactly. Okay. On the outline that I gave you for your test, okay, notice item number 6. Item number 6 is to draw this arrow diagram. And actually, if you draw the arrow diagram on your test, you can use it as a tool. So that's kind of why I have it there. Okay, so how do we draw the arrow diagram? Well, it's kind of got the whole row thing going, okay, and it's kind of got the column thing going. So the first one only has 1 row and 1 column, 1s. And then we go to the n is equal to 2, and we make a new row, and our s's line up. So underneath the 1s, I put 2s, and then I make a new column, 2p. And then I go n is equal to 3, I go 3s, 3p, and then 3d. Okay, so these are just 3 different rows, and my columns are lining up just great. Then I go n is equal to 4, 4s, 4P, 4D, and 4F. Now, we could go G and H and all that, but we're done with adding columns. We're only going to have 4 columns. But I do this until I get to n is equal to 7. So 5 looks like this. 5S, 5P, 5D, 5F. I don't do the 5G. 6 looks like this. 6P, 6D, 6S, 6P, 6D, 6F. And I end with 7. 7S, 7P, 7D, 7F. Do you guys remember a while back I was saying about the new elements that were discovered? Created. Okay, and actually we are ready to start period number 8. See, francium is period number 7. Okay, now we're ready to start period number 8. So when we do that, or when they do that, we're going to have to adjust our arrow diagram. So those are subshells. Well, where are the arrows? Well, here's the arrows. They're diagonals, actually. Okay, so the first arrow, oops, my builds are kind of messed up. Oh, technology. There it goes. No? Oh, come on. Maybe I'll do it this way. Okay, there we go. So the first arrow only catches one subshell, and so does the second one. This is where I think it's hard. If you've made a sloppy set so far, it'll make it hard. The third arrow catches 2 subshells, 2P and 3S. And then I catch 3P and 3S, and then I catch 3D, 4P, 5S. Okay? So once I get started, it's not too bad. The last diagonal only catches 1 subshell. Now you'd be like, what's the point of this? Well, each arrow actually represents a one or a set, in some cases, of orbitals that have the same n plus L value. You guys told me, or I told you, or we worked it out together, that the 3P and the 4S, 3P and the 4S have the same n plus L value, and they do. They share, actually, the first kind of set of arrows. Okay? So all this is to say is okay. So what I've added now in black is for that arrow, for that diagonal, what is the n plus L value? Okay, and again, if you want to go ahead and acting dumb. All right. So this isn't working. I mean, this is working, but this isn't working. So bottom line, we do the first diagonal, we do the second diagonal, we do the third diagonal, we start at the top, go down. The fourth diagonal, start at the top, go down. Okay, and I'll kind of show you how that works. This, I think, is a figure from your textbook. It's similar to what I did, but just kind of a little different. I like my box and arrow diagram better than this one. Okay. Just being dumb. So let's do one. It's easier to show you. We're going to pick on potassium, and we're going to do the spectroscopic notation instead of box and arrow, because that would drive me nuts. So the first thing, if somebody asks you, how are the electrons configured, you have to use a periodic table, find potassium on the periodic table. It's atomic number 19. Okay, so we need to find homes for 19 electrons. So the way this is going to go is actually I'm going to highlight up here in this arrow diagram what we're finding down here. So we're on our way to 19. The first 2 electrons, we do the first arrow and they go in the 1s. So it's 1s2. We go on to the second arrow, and all that's on the second arrow is just 2s. And how many electrons can you fit in a 2s? Well, 2. So my superscript's 2. So I'm on my way to 19. I've got 4. Then I go ahead and go to the top of the third arrow. So that's 2p. How many electrons can we put in a p-type?
It can hold 6.
It can hold 6, exactly, total. And we're on our way to 19, so we need all that room. Yep. So here we go. So 2p6. But now I need to finish that arrow. See, we're on the third arrow. And I need to finish that arrow and go to the 3s. Okay? And how many electrons can I put there? Just 2. So it's 3s2. What? Oh, darn it, sorry. Oh, yeah, that's like 3s2. Now, before I go to the 3s2, anytime you hit a P6 like we did there, okay, you have bumped up against the end of the period. You are at that last group. That last group, group 8A, are called rare gases, inert gases, noble gases. They actually have 3 names. Now, in a minute, I'm going to show you how you can use that to your benefit and come up with an abbreviated way to say how the electrons are configured. So there's neon. Yeah, now we go to 3s2, like I said before. Okay. Now we need to go to, what, the 4th arrow, but we go to the top. So we go 3p. How many electrons can we put in a p-type? 6. So I'm going to go 3p6. And notice I have bumped up against another rare gas. Which rare gas is it? Well, I bet it's the one right underneath neon. Okay? Which is argon, the pirate's favorite element. Okay? So now where do we go? 4s. Very good. And this is where sometimes students want to go to 3D, but it's not. It's got actually a higher n plus L value. So 4s and 4s2. I'm liking it. Oh, why isn't it 4s2?
Because you're only putting 1 electron.
Very good. Yep, we only needed 19 electrons. And like JC said before, we know where we're at if we go ahead and add up these superscripts. So let's see. Well, I've got 10 electrons there. I've got 18 electrons there. That makes sense. 19 electrons. We're done. Does that work for everybody? Okay. Well, that was 19. Let's do 40. And I won't belabor this one as much. How's that? The first 2 electrons go in the 1s, so we have 1s2. The next 2 electrons go in the 2s, so we have 2s2. The next 2 electrons go in the 2p, so we have 2p6. And by golly, we have reached a rare gas. Hallelujah. It's going to seem like deja vu. The next 2 electrons, according to our arrow diagram, after the 2p, we finish that arrow and go to the 3s, and we can only accommodate 2 electrons. And then we go up to the 3p, and we can accommodate 6 electrons there. So 3p6, and we've reached another rare gas. That's argon. So this is feeling very familiar. So now we go to finish that diagonal. We go to the 4s, and it'll be 4s2 this time. We need to fill that up entirely. Now where do we go?
3D.
3D, very good. And how many do we put in there?
It can hold 10.
It can hold 10. Do we need 10?
Yes.
Okay, good. We need all 10. Because I was at 18 after 3p6, that made 20, and then another 10 will make 30. What element are we at then with this configuration? See Tyler getting out his, or Jeremy, excuse me, getting out his periodic table. We're at zinc? Very good. We're at atomic number 30. Perfect. Okay, so now where do we go? We need 10 more.
4p.
4p, and how many are we going to put there? 6. Very good. 4p6. We must have arrived at the rare gas underneath argon, which is krypton. So we said this was 30, so we're at 36. Wait, is that right?
Yeah.
Okay, good. So we only need 4 more? Okay, so where do they go next? 5s. And how many? 5s2. So I need 2 more. Where do the last 2 go? They go in the 4D. Very good. 4D2. Perfect. So what what this arrow diagram does is kind of help unscramble things a little bit. So That actually is in what we call the order of filling. See the green caption, in the order of filling. Sometimes it's helpful to re-look at that same electron configuration and unscramble it and rearrange it in what we call the order of increasing n. So let's look to see how these two are different. My pen's not working, but... Last time I say we get out early. Dang. Kiss of death, kiss of death. Okay, ready? Let's look at another one. That was 40. Oh, is this where I have a... This is 53 now. Oh, ready? We could do this. 53. It's going to look just like 40 with 13 more electrons. Okay? So we have 1s2, 2s2, 2p6, and we're at neon. And then we have 3s2, 3p6, and we're at argon. Yep. And then we have 4s2, and I'm going all the way through the last one we did. So 3d10, 4p6, and we are at krypton. Then we go to 5s2 like we did before. So we are on our way to 53. Looks like we've got 36, 37, 38 there, right? So we're going to have to completely fill the D type. So how many electrons can we put in 4D? 10. I'm liking it. So then be 4D10. And if we add these up, we're at what, 48? And we need to go to 53, so we need 5 more. 5 more. Where do they go? 5p, exactly. So 5p5 finishes it off. That's it. So this is what we call in the order of filling. So in the order of increasing n, it looks like this. I'll call this off for you. How's that? Increasing n. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, then 5s2, 5p5. Bingo! So we just kind of unscramble it. So one more thing I want to mention before I actually have an assignment to give you is this whole rare gas thing. So we said that we bumped up against a rare gas anytime you see, this is in the order of filling, anytime you see this P6. So 4P6, if you find period 4 is potassium, 4, at the end of period 4 is krypton. So I know 4p6 actually, that is krypton. So the abbreviated rare gas notation uses that to our advantage. Now this isn't going to work. So in the abbreviated rare gas notation, we simply kind of ball all of those up and it looks like this. So we ball everything up from 4p6 back to the beginning, and we put it in we put Kr in brackets. So all we have to account for is these guys on the end here. After bracket Kr, all we have to do is bracket Kr 5s2, 4d10, 5P5, and you're done. Now I know down here in green, my slide went ahead and scrambled it as increasing n. I would leave it as it was added, because that's the way I think of it, so either way. Any questions about that? All right. Boy, I hope this works better next week. It is Friday, you know. So there is an assignment slide we did get to today, but I did do these. Did pull this up for you guys to have something to do this weekend. So this will be due on Monday. And the first part says using spectroscopic notations. So you guys know what that is. The second part says use box and arrow notation. Wait, no it doesn't. Sorry. Spectroscopic, yeah, box arrow diagram for the second one. The third one is spectroscopic notation. You can use the abbreviated. And the bottom one, if you want to start at the bottom, you can. Number 4 asks, one of the things I said you can do on your test is to draw the arrow diagram. So feel free to do that first. All right? Have a good weekend.